Hello everyone, I am Sohanjit Ghosh, a fourth year PhD student in mechanical engineering at Johns Hopkins University, and I work with Professor Ryan Hurley. I'm going to talk about my thesis work on rapid compaction in granular materials, in situ experiments, and mesoscale modeling. So let's get started. Impacts on granular materials are very commonly observed in nature, and often a large fraction of the impact energy is utilized in the compaction process. So it's very important for us to understand the rapid compaction in granular materials. The image on the left clearly provides a schematic of all the different mechanisms that goes on when a projectile or an intruder impacts a granular material. We have things like granular flow, dilation, expansion, compaction, and fluid coupling if the granular material is saturated. Now, this compaction can occur over the range of velocities. On the lower end of the spectrum, we have applications in the pharmaceutical industry like powder compaction to make pills, while at the highest of the velocity scales we have impacts in the order of few kilometers per second on asteroid surfaces, which are often covered by regolith. So when we look at the region directly beneath the impactor or the projectile, it is almost like a uniaxial strain problem, and it is almost a planar impact. And different deformation mechanisms are activated. Things like first the pores or the voids between the grains collapses. It's also called pore collapse. There is frictional interaction between the grains. There are defects that are being generated for metallic grains. There is fracture for brittle grains, and as we go to higher and higher velocities we also have things like melting, jetting, chemical reaction between the grains, and bonding. So our goal is in this work is to identify all these different deformation mechanisms that are going on during rapid compaction. As you can imagine, when I talk about impacts in the range of kilometers per second, the time scales of the processes are very small, often few hundred nanoseconds or microseconds, and the process, like due to the high kinetic energy, is often very destructive in nature. So traditional gas gun experiments like high velocity impact experiments use free surface velocity measurements like photon Doppler velocimetry, but that will not give us in situ information that we are interested in. We want to understand what's happening inside the granular assembly in between the grains. While tomography, something like X-ray tomography, it's a very slow process, and it takes time and cannot be used in a destructive settings. So that's why we look into the ways where we can perform this in situ imaging to visualize the compaction process, and also we'll see like how we can like complement our experiments with some mesoscale modeling to get the full 3D kinematics and kinetics of the grains as they are compacting. So for in situ measurements, we utilize X-ray imaging to understand what's happening inside the granular material and in between grains. We performed our experiments at this facility called dynamic compression sector, which looks something like this. This is actually a synchrotron source, as they call it, where you have the X-ray beam coming in, a very powerful X-ray beam coming in, and at DCS you have a gas gun setup and a X-ray imaging setup like synchronized together, such that when the impact happens, this X-ray system can take 8 frames, and the time gap between each frame is 153 nanoseconds, which is really fast. The major advantages of going to a synchrotron facility as is that it gives a parallel beam, and also it is a monochromatic beam as opposed to traditional X-ray tomography like cone beam setup. So in a nutshell, what we do is like we pack our granular materials in a box. We have a polymer box where we fill sand grains, for example, and then we the first a very important step is CT scanning it so that we know exactly where each grain is, what their shapes are, and the granular assembly. And then we take it over to DCS where we like put the sample in the gas gun, we align the cameras, and then we finally there's a projectile that comes and hits our sample at our specified impact velocity, typically in the order of 1 to 2 kilometers per second, and then we are able to also get X-ray imaging at the same time. These experiments were performed in 2019 by a former graduate student, while I did most of my experiments in 2022. We varied the sample material over three different types. We had more brittle soda lime glass and sand, while also we also had like a ductile aluminum powder. We varied grain sizes from a smaller 355 micron range to higher 500 micron range. We varied the impact velocity. We um, had different depths of sample. For example, a single layer had only one layer in the x-ray direction. We also looked at different regions of the sample, and this chart provides a summary of our experiments and our experimental efforts. So at the end of the experiments, we get a series of eight images, and this is what it looks like. When you stitch them together, we can see the grains getting compacted. Although qualitative, we get very important insights into the compaction process. The video on the left, we can see something called the compaction front, which is the front of the compacted region or the dark region in the X-ray images. When we look closely into the monolayer samples, we also see um, that at a at very high velocities like 1.8 kilometers per second, we can even capture the melting between the grains, which arises due to a very high kinetic energy deposited in the granular contacts. And if we look closer in our soda lime glass grains, we see like there are few fractured patterns or signatures that we can find in the grains, while for aluminium we can observe a very clear plastic deformation between the filling the voids. XPCI imaging is very good to give us in situ information, but it is on gives us only 2D snapshot in time, therefore very qualitative and limited information. But there are useful things that we can do with this. For example, we can track the progression of compaction front. This is very important, and it is quantified very popularly for solid materials. It's called the shock Huguenot, but we can do something very similar for granular materials. On the other hand, if you are interested to look at pore size evolution, we can actually see how the pore sizes are evolving with time as the compaction happens. But these experiments by themselves are not enough to understand what's happening entirely in 3D. That's why we need to combine and supplement these experiments, or rather complement these experiments with some modeling that I'll talk about next. To create a mesoscale model, we first generate a mesh out of the original CT scan that we did before our experiments, and we basically try to make a digital twin of what's happening in the experiment. So we have an impactor coming and hitting granular materials enclosed in a box. For our material models, we choose very simple models for metals like Johnson Cook, and for brittle materials, for now we assume it's perfectly plastic, and we have a temperature model, a volumetric response as the migration equation of state, and we set up a finite element simulation in Abacus Explicit. From the mesoscale simulations, now we are actually getting some quantifiable information, things like stresses, temperature, pressures, strains in the grains, all of the quantities that are of interest to us. But the simulations don't mean anything unless they are validated. That's where again the experiments come in. So we perform a strict validation process to make sure our experiments and simulations are like apples and apples to apples comparison. Validated mesoscale models gives us access to the 3D kinematics and kinetics of both the grains and the pores, and can be used to study things like quasi-static to dynamic transition and pore collapse. These are well researched topics in the community. We see the heterogeneity that arises in the granular assembly, in the stresses, temperature. We also can quantify the pore size evolution in 3D now, whereas before using X-ray imaging, it was just a 2D projection. To sum up our work, we saw how X-ray imaging provides key insight into all the processes and mechanisms that happen inside the granular assembly, which is really cool, I feel. The second thing, we saw that experiments themselves are not enough. That's why we need to combine them with some mesoscale models to understand what's happening in 3D. So we get full time 3D time resolved information now. To look at some of the future work, we can extend this to other heterogeneous materials like concrete and sandstone. This is not limited to only granular materials. And also we saw there is so much heterogeneity, so incorporate this heterogeneity in some of the constitutive models would be really great. Thank you for listening. Acknowledgements to my funding sources and collaborators.